All right. Thanks, everyone. My name is Rob Cowart. I am the founder of a company named ElastiFlow. And so what ElastiFlow is a solution to capture data about network traffic flows. So it collects like technologies, Netflow, S-Flow, IPFix, and also some things like AWS VPC flow logs, and other data that essentially is saying, who's communicating with who and what are attributes of those conversations. I'll share a little bit more about the data in a minute because it's really relevant to the conversation we're going to have here. This is actually an interesting meetup for me to speak at because the very first meetup I ever spoke at was at a Elastic meetup here in Munich. And at the time, I've been in like network observability technologies over 25 years, pretty much my whole career. And if you think back to the 20-teens, 2013, 14, in that time period, there were all these new data platforms coming out. Elasticsearch, InfluxDB, MongoDB, all these NoSQL databases. And organizations that I was working with, customers I was were starting to be like, I wonder if we could use these for these use cases that we traditionally paid other vendors lots of money for some proprietary solution. And so I started experimenting with that. And the result, one of the things I experimented with was taking these network traffic flow data and putting it in Elasticsearch. And it was kind of got some interesting results. And so I came to an Elastic meetup and just kind of shared what I had learned. And then someone said a question, they said, is this available for download anywhere? And I said, well, no, but I guess I probably could do that. Let me get back to you. And I actually looked up the comment where I said, you can see it's over. There's a few days ago, I made the screenshot, so it's probably more like 2,460 days now. But I'd actually then put it on GitHub and I named the repository ElastiFlow. Fast forward a few years, tens of thousands of organizations around the world were using this. And I said, maybe we can make a business out of this because it was really just a science project. And so we, back in 2020, kind of rewrote the whole thing from scratch, released it in 2021. And now ElastiFlow is actually, as of tomorrow, 2 new people are starting. We'll be 26 people in 4 countries with a pretty significant set of logos that use our solution. And Elastic is a big part of what we do still. And so I guess my message in saying all that is to say, if you ever thought about speaking at a meetup, do so. You never know when it's going to be a life-changing experience because that's what it's became for me and my team. So what I want to talk about today is TSDS, time series data streams, a feature added around G8 around March last year. I think it was 8.7 of Elasticsearch. Anyone heard of that? Yeah, have you tried it yet? So I'm going to tell you, this is one of those things. I'm gonna pick at the Elastic marketing team a little here. It's like, we read that and I'm thinking, oh, that is going to be awesome. And you'll see why I think that in a second. But it was like a little footnote down in the release notes. Oh yeah, and GA of TSDS. And I'm thinking, y'all need to be shouting about this, and you'll see why I think as we get into the presentation. So the data we're going to talk about, just share a bit, is again, network traffic flows, essentially who's talking to who and what are the attributes of those conversations. And so it's very much like source IPs, source port numbers, destination IPs, port numbers. You could get the same type of data like out of a firewall log. So a lot of what I'm going to share here could also apply to any type of logs that have a timestamp and a set of attributes and metrics related to those logs that you want to be able to efficiently store and analyze. So I'm going to talk about network traffic flows, but it is a very these techniques could apply to other things as well. By the way, just a quick about our solution and where it's used for. If you know who's talking to who and the attributes of those conversations, there's a lot of things you can do with that data. The traditional one is kind of performance and availability related. So, you might have some metrics that tell you this network interface is 99% utilized. What's the very next question you probably have if you're looking at that is, I wonder what's driving that utilization. That's exactly something what Netflow data can tell you about. kind of related to that then, it would be things around capacity planning, or what we're seeing a lot of is cost control. You've just like taken your on-prem app and, migrated it into AWS, and finance gets the bill and they're going, yeah, compute this. What is this incredibly large unexpected number for cloud egress network traffic cost? And what's the next question they ask? I wonder what's driving all of that egress traffic. That's exactly what we can tell you, either from on-prem, who's pulling that data down, but also running in the cloud environment itself with like the VPC flow logs. And the final area where we've seen a ton of growth in the last couple of years is around security, because if, again, who's talking to who and what are the attributes of those conversations, you can do things like detect brute force logins or reconnaissance activity, horizontal motion, like we see that someone SSH'd into a box, and then from there was a whole bunch of SSH sessions to other boxes. So they're trying to move horizontally, bad actor, move horizontally in an environment. And that is, again, how this data can be used. So our core product is around making the most out of the data that we get from the network. And then we see Elastic as a really great platform for what we say exploring. You'll hear our team talk all the time about the explorability of the data that's allowed by having a search engine as the underlying data store. And so we send that into Elastic. We also support Kafka and some things like that, depending on what you might need architecturally, especially at certain scales to do. But ultimately that lands in Elastic, and we provide dashboards, over 120 machine learning jobs, alerts, all of that's all pre-canned. So it's literally install our collector, point it at Elastic, point your devices at our collector, import dashboards, import ML, import alerts, and you're up and running. We last quarter actually together with Elastic, we won Procter & Gamble in the US as a new customer. And their person inside said to us, that was Elastic Cloud, by the way, so it was really easy to install Elastic as well. They said to us, wow, that was the fastest vendor onboarding we've ever had. So it was so it's a very designed to be very turnkey. But let's get into the challenges. So, and why TSDS is so interesting at scale. So once you get these records in with all this information, you start to enrich them with things like geolocation, maybe add some business context in, and you get that, typical JSON explosion, if you will, that happens. What we actually have seen, this was one of our test environments. We'll get a little bit more detail into it later. And I do want to say these metrics, we always, when we're doing these measurements, we always ingest the data, stop ingestion, do a force merge to get it so that we have consistently, we're always measuring the same numbers. And so indexed in Elastic, the records with this particular data set were 572 bytes per record. So you just do the math, right? Times 32,000 records per second, 86,400 seconds in a day. And you get up to 1.5, a little over almost 1.6 terabytes per day. Oh yeah, but you need high availability, so you do replicas as well, and now you're at over 3 terabytes of data a day. Now, 32,000 records per second, I would say, is probably about the median. We do have we built clusters up to 1.2 million records per second. You got to pay attention to a ton of detail when you do that. That could be another good talk all by itself when you care about things like memory latency and memory bandwidth and all of the, everything matters at that speed. But typically, we have some small ones as well. Typically, we'd say that's about a median customer, 32,000 records per second. So that volume of data can obviously build up, especially if you say something like, well, I want visibility for 60, 90, maybe even a year of data. Well, that would be quite a lot of information that you have to have stored. So if you can optimize that, that can obviously help you quite a bit. Now, one of the things, how many of y'all worked with time series databases in the past, right? So one of the things that time series database helps you to do is to structure the data so that any of your interactions with it, as long as there's a time dimension, like, last hour, last week, between these dates, whenever there's a time dimension, the data is stored or in an optimized way for those time-based queries. And so Elastic really didn't have that in the past, that type of, you could store time series data, but it wasn't really optimized for time series data. So what time series data streams does is it introduced a few features that allowed for this time series optimization. A few things they did is they first did implemented index sorting. What's really interesting, by the way, is these numbers, this 30 and 40%, was our testing. When y'all first brought it out, it didn't have that in the docs. It has that in the docs. I would just say our testing directly confirms what they say too. 30% comes from sorting by timestamp, 40% comes from using synthetic source. It's exactly the same results that we've had, so I can confirm they're not, being optimistic in the docs. That's exactly what we saw. So, so by sorting on timestamp is one thing. So that way, when you do a query like the last hour, well, literally the last hour of data is indexed or stored together so that it's a much quicker query than having to, sweep over the entire data set to find those records. They did synthetic source. Anyone familiar with synthetic source? I know the Elastic people are familiar with it. Okay, so basically when you store a JSON document in Elasticsearch, it will index all the fields, but at the same time, it also takes the original JSON document and stores it in a thing called _source. Now you could turn that off, but if you ever want to retrieve the actual values for an individual record, you need the source document. And what synthetic source says is we're not actually going to store the original raw document, but rather from the indexed values, we're going to rebuild the source field at query time so that you don't actually have to store it. You can get to the same end result by rebuilding it from the index stuff. So that's, again, a savings that you get. There's one other element to this. So we also find this is a pretty exciting part of time series data streams is you have the ability to now do downsampling. So downsampling is basically where you can say, take the last 30 minutes of records that are all related to the same time series, give me like a min, max, average. You have a few different ways you can pick how you want that represented. And then it will aggregate that 30 minutes into a single record. And so if you think about, instead of saying, I want a year of raw data, that would be a lot of data, you can say, I want 2 weeks raw. Then I want another 30 days, 15-minute aggregations. Then I want up to 90 days and 1 hour aggregations. And from there out, I'll take 24-hour roll-ups for the whole rest of the year. This is very typical in our field of network observability. This is based on the idea that the granularity of data loses value as the data ages. And so you can typically do this downsampling and save, again, a lot of storage space. And that's something that time series data streams also brings. The challenge is this, though: to efficiently do downsampling, you need all of the data for a time series on the same shard. And so that way it can be a very efficient process that's generating those new records. And so that's kind of the third major piece, I would say, of TSDS for it to work effectively. So what does the data have to be stored in a time series database? It has to have a timestamp. Typically, this data is like long series of a limited number of time series. So think of this as like, I have 100 servers and I want CPU utilization every minute across all 100 of my servers, and I want it for 90 days. So you got like this long 90-day time series. And okay, you might add a server or take a server away, but it's always about that same consistent number of time series. So it's typically long series at a very regular interval. You'll also tend, this type of data also tends to be characterized by a few, we'll call it tags, is what InfluxDB might call it. Labels, I think, is what Prometheus says, or you have dimensions, as Elastic would call it. But basically, these pieces of information that say what it is. So if you think of CPU utilization, it might be the server name, and maybe it has 2 CPUs in it, so like server name and CPU ID, something like that. And then you'll have a whole bunch of metrics like utilization and Maybe there's the different idle time, system time, user time, and a whole set of metrics that are associated with that. So that's another characteristic of the time series data. And another thing, and this one's going to be really important here in a second, is it's typically of limited cardinality. So historically, most time series databases struggle when the number of time series they have to manage grows to be a very large number. And so we actually have had issues in that with other things we've stored data in. So because our network traffic flows, so if we think about those characteristics, do network traffic flows have a timestamp? Yes, they do. All good. So that was going to be easy. Are these series long and at regular intervals? Well, no, not really. Let's take, for example, you're watching a Netflix movie, and through your network device, we're getting flow records. Well, if it's a 2-hour movie and your device is configured to send an update about that flow every minute, you're going to have 120 records. The movie ends, the time series is over. And then you start watching the next, oh, it's a new time series, right? So, and so what you tend to have is a very high cardinality. And flow data, you think of, there's this thing called 5-tuple. It's basically source IP import, destination IP import, protocol. That's kind of the bare minimum of identifying a session. And so just sitting at home browsing the internet, I've tested this actually with InfluxDB. Just sitting there browsing the internet, after about a week, I had a cardinality of nearly 200,000. And most people would tell you InfluxDB falls over about 1 million. By the way, I used to work for Influx Data for a while, so I can confirm that that is true. And so, imagine now an enterprise with, 2,000 users and hundreds of servers, and they're all going out to the internet, and all that flow data is coming in. You can have literally millions and millions. We have one gaming customer, Demonware is their name. If you ever, they're part of the Activision family. If you ever play any of the, whether it's King or some of those others, if you're into gaming, and like the whole login process and validating your credentials and all, that's Demonware. And so they're one of our customers, and we've seen some of their data. They'll typically see like 1.5 million unique IP addresses in a half hour. So imagine how much cardinality they have in their flow records. And they tend to be, again, you log in, boom, it's over, time series is finished. So it's a very short time series. When we think about also a few consistent tags, it's actually exactly the opposite. In a flow record, we have 2 primary pieces of metric, bytes and packets. And then you have a whole bunch of tags, like the source, the IP addresses, the port numbers, the protocol, maybe class of service queues. You've enriched with some GeoIP, like there's tons potentially of dimensions, but there's only a few metrics. So it's kind of flipped from traditional time series data. And then the final thing is cardinality. So is it limited and consistent? Yeah, not a chance. Like I said, extremely high cardinality of data. Now I picked on InfluxDB here a bit. I have to think about this because Philip's recording me. I probably don't want that out too much. But anyway, they came out with their thing and that's now their version 3. It was originally called InfluxDB IOX. And they said unlimited cardinality. And the very first thought I had when I saw that, I said, yeah, we'll put that to the test. Because again, when you're talking 20, 30, 40, like what does unlimited mean? Yeah, it's a challenge, that's to say the least. All right, so as it turns out though, we found Elastic and these high cardinality data sets actually works really well in our case. That's why it continues to be the core of the solution that we deliver. Some of the things we also had to think about were how we set these dimensions. This does matter. There's something called a TSID, and that's actually the other field that its time series is sorted by. So you sort by timestamp and by this TSID field to allow for efficient, effective querying. And then there's this thing, because I mentioned you had to be on the same shard if you're going to do downsampling. So there's this thing called the routing path. And the routing path was the largest challenge for us, because if you were to say, let's just take like a TCP connection. what would you say represents a session in TCP? Probably like source IP, destination IP, port numbers, and protocol at a bare minimum, right? What about an ICMP exchange? Like you ping something and it responds back, ICMP, whoop, no port numbers. So we don't have those values. What about IGMP or SCTP or DCCM, or pick whatever list of 100 different network protocols that you might care about that all have some different form of um, thing that represents a session. So setting this this routing path to make sure sessions all got to the same place turned out to be a real challenge. And the reason it's important, if you set that field unwisely, and we encountered this in our very first test of TSDS, if you set that unwisely, what happens is one shard, like we first said, let's just do it, the device that sent the flow record. But then you have one device that sends a whole bunch of records, like some big core router with a bunch of virtual interfaces that's sending like 20,000 records a second. And then you have 100 smaller devices sending 100 records a second. Well, that 10,000 is all going to be going to one shard, and you're going to have this hotspot, and that one hotspot is going to overall limit the total throughput that you can have in the cluster. So we actually implemented TSDS the very first time we tried it, and performance just sunk in the basement. Why? Because one node was maxed out at 100% and one shard on one node. And went, okay, that was a bad idea. Let's try this again. And so we experimented around, and we kind of set these basic fields. These are ECS fields here. These basic fields is like the core of what would represent the ID. And then on the routing path, what we actually did is inside of our collector, we wrote protocol-specific algorithms that pick out the different values that represent a session for that protocol. And then we put them together and make a hash. So that so we only really have to have one field be the routing path, which is, we put it in this TSDS routing path key. And so we only have to define one field as the routing path, and the value of that field is built every time in a protocol specific way. So we don't have to then worry about whether certain fields are there or not there or what have you. And because it's only one value, it's also a little bit more efficient for Elasticsearch to process that value when it's making its determination of where to send that record to which shard. Make sense? Yeah, so that was probably the big aha moment, was that one, a network session is a time series, and we can build session IDs for a routing path in a protocol specific way that we had to put into our code to do that. And that really allowed us to achieve a lot. So let me give you the results of what we were able to achieve. So our test environment, because I always think it's good to level set on the test environment so we all know what we're talking about. So we actually tested on a 64 core AMD server, 256 gig of RAM, NVMe SDs, actually probably oversized for what Elastic would tell you is the typical Elasticsearch node. But we're running on this, both Elasticsearch, Kibana, and our collector all together. And we took one of our test data sets. We actually used one from the gaming environment I told you about, because we knew it had really high cardinality. And so this is 32,000 records a second, which is, I don't know, would y'all consider that high for a single node? 32,000 a second? Atypical, or is that about right? Y'all don't know? No, I don't know. I was just curious. The most we've had in one node is 400,000 per second. But
it sounds good. Like I think we've seen worse.
Yeah, okay. I mean, it's when you get into that scale, though, like I say, you're definitely, that's probably a whole other meetup. Just how do you build hardware for that kind of environment? Okay, so let's get to what the results were. Again, this is just what I showed you before. So just a recap real quick of, post forced merge, the results we got, it was 572. And what this exact same test set did with TSDS enabled, boom, 177. So we dropped from 316, I think I have a side by side here, there we go. So from 572 to 177 bytes per record, all the way down without replicas to 489 gig from almost 1.6 terabytes. And of course, significant savings with the with replicas as well. We actually have one customer right now that is saving about, from their words, a little over 10 grand a month in storage cost. It made me think, man, we should have like charged real money for that feature. But anyway, they're saving about 10 grand a month in storage costs because of being able to enable TSDS. So, it's not just something that, is it kind of a nice to have, but at scale, you can be talking about saving real money. So we have been super excited about TSDS and literally sitting back going, I can't believe they're not screaming more about this. This is the coolest, most valuable feature, that we've seen in a while. Of course, recently you've had that Gen AI stuff, which is kind of cool too. But all right. So let's talk about, are there any downsides to enabling TSDS? It's always fair to give both sides. I wish there was a little more contrast. I apologize, but on the top slide without TSDS, we're a little under 30% CPU utilization on the box at that rate. And then on the bottom, once we enable TSDS, it goes up to a little bit over 30%, typically 5, maybe 7% increase in CPU utilization. This is due to, as you ingest the data, it does have to sort. Now, because it's sorting on the time dimension and the data is coming in time order, basically, it's not a super heavy duty sorting process. But there is a little bit of CPU hit. However, I'd probably trade 5 to 7% CPU for 70% storage savings like any day. The only thing I would say that that you do have to pay attention to, and again, this box was under a pretty consistent 32,000 per second load, is when we do queries, the exact same data set in non-TSDS. And by the way, I should probably preface this. This test was done with our most challenging query in all of our dashboards. It is 7 layers of nested Elasticsearch aggregations. So this is not typical. I literally, because I wanted to see the difference, I took the absolute worst case scenario of anything we do. And so it's like literally, like I say, it's a table with like 7 layers of nested aggregation. Without TSDS enabled, it was almost 37 seconds. With TSDS enabled, it was almost 65 seconds. So there is a query side performance hit that's worth, making sure you think about. As I was doing this, as I was preparing this deck though, there was a new release of Elasticsearch, 8.12 it is. And again, had a very interesting feature around queries. Anyone know what it is? Huh? No? Concurrent, there we go. So query phase parallelism. So as soon as one of the things we've always found kind of curious is we've always felt that the when a node, and this is always the caveat, when a node is under a heavy ingest load, the query performance always seemed unusually high given the amount of resources that were still available on the server. Now, part of that has to do with the read latency of SSDs when they're being actively written to. Intel Optane used to be awesome for that, by the way. You have almost no read latency penalty. They used to be awesome for what we used to call them blazing hot nodes. But the other thing, by the way, when we did all these query tests, the reason we had so much RAM in the box is we wanted to make sure all the data was in page cache. And we actually did confirm as we were doing the testing that that there were no disk reads. It was literally reading everything out of the page cache, because otherwise you could get results kind of start to get weird. So, but we always thought that's kind of weird that given the amount of available resources, you'd think there was still some more to give, And then I saw this feature and I'm like, oh, wow, I never realized Elastic didn't do that to begin with. And so I said, this might be interesting. So now, unfortunately, I didn't capture the numbers for when we had TSDS enabled. But on the non-TSDS, again, we had almost 37 seconds. And then we immediately updated the box from 8.11.4 to 8.12 and ran the test again. Now, this on the single server, it had 2 shards. And immediately we jumped from 37 to 29. I should have also said this earlier, but these were actually not just one test. We ran it a couple times and get an average. Now, we didn't run like 12 times. I think it was 3 runs on each, but nonetheless took an average. So we went to 29.3 seconds, already a nice improvement, I would say, and said, I wonder if we increase the shards, how much of it? And then it was like, boom, almost down, cut that again down further. So I'm kind of, even this test made us think, I think we're going to start recommending to customers that 4 shards is the right number per server, at least for our data sets. Always test your own data, always test your own data sets, but for our data, that might be kind of a good sweet spot. So anyway, so that's not TSDS related, but I thought I'd throw it in because we tested it as we were preparing these slides.
So
Yes, sir.
before the non-TSDS data was a set of 3 terabytes, more or less. Is this correct?
Well, that was theoretically, if you ran it for 24 hours, what would be the total volume of data? Yeah.
But in this case, it was not that.
We actually ran it for 2 hours and then did a last 1 hour query. Right?
No, it was just about
Yeah.
what is the average size of the shard?
Oh, right.
It
Yeah.
didn't explode, I imagine.
Well, yeah, I guess you could do the math. So it's probably going to be about 3.7 terabytes divided by 24 or divided by 12. That'd be how big it was at the time.
Do you expect better numbers with TSDS when using the disks instead of the memory? Because there's less to read from the disk?
Maybe. It's something we've thought about, and I'd say maybe because I haven't tested. In theory, you're right, because you would read less. You still have to convert that with the synthetic source to have the source. But if you actually were hitting disk IO, you may see a benefit versus hitting the disk just because of the volume or having to read off of it. It's possible. Yeah. Okay, that was basically my last slide. Hopefully you found that useful and maybe made you think, man, we got to try that ourselves. Because like I said, we think it's an awesome feature. I mean, it's a way that if, if your data allows you to leverage it, let's face it, that's storage savings, that's real money. Then thank you very much. I appreciate the time, and hopefully I was able to share some good information.
Hi, this is Julia from the Amsterdam Elastic community. If you like this recording, you can join our local meetup groups for in-person events around you, and hope to see you in our offices soon.